Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit Kinetic Theory of Gases. So let's begin with the KTG. It's a kinetic theory of gases. This is one of the very exceptional unit of physics. When I say physics of class number 11 and class 12, that it is the first unit where we need to assume something. We need to have a certain assumptions, and then we can proceed with the theories. All this assumption has been practically verified, and then we understood that yes, these are the correct assumptions. We can use it because that can be verified. That cannot be proved, but this can be verified. So this is one of the unit, and one and only unit which is having certain assumptions. And first we will study this assumption, and then we will study their theories. So let's assume something, and then we will understood the situation. So first assumption of KTG, it's a kinetic theory of gases. It's that gas consists of a large number of tiny particles, and these tiny particles are known as the molecules. As you can see this in an image, that many of these smaller balls, in reality these are not the smaller balls, these are the molecules of the gas that are traveling in a very random fashion. You don't know that which one will go in which direction. So this all large number of tiny particles are known as the molecules of the gas. Collision among or between the particles and the containers of the walls. As you can see, this particle are being collide with the walls of the container as well as within themselves as well. This collision will be always considered as an elastic collision. And when I say there would be an always an elastic collision, it means there is no net loss of total kinetic energy. So no loss of kinetic energy would be there. 100% kinetic energy would be conserved. A momentum is always conserved, that you understood. For next, there are no forces of attraction among gas particles. So you are not going to apply a force of attractions between these molecules. Next, all the particles of same gas are identical in all aspects. Please do understood this. They said all the particles of the same gas are identical in all aspects. So let's understood that in this container I have a molecules of H2O. It's a molecules of water. So when I say it's a molecules of H2O, look at this. Every molecule is same to the other one. Second, let's suppose these are the molecules of CO2. It's carbon dioxide. So look at this. It is identical. Yes, it is not going to combine, or it is not going to match with the molecules of H2O, but every CO2 molecules are equal in nature. I hope you understand this, what I mean to say. If I merge this, if I merge this, it is the molecules of H2O plus CO2. Then this green one, this green one are the molecules of H2O, and this oranges one are the molecules of CO2. So this is the next assumptions, that all the particles of the same gases are identical in all aspects. I hope this is clear. Next, pressure is constant in all the directions. When molecules are there, when molecules are there, whether they are moving, whether they are colliding with themselves, or whether they are colliding with the walls of the container, the pressure is same in all the directions. Please do understand this very well. Next, gas particles are continuous, rapid, and are in random motion. Please have a focus on this word. It's a random motion. Therefore, they possesses a kinetic energy, which is energy of motion. Yes, they are having a motion, and that energy, that motion itself represents that they are having certain amount of kinetic energy. But one more thing, that they are moving in random motion. And when we say that they are in random motion, That means we don't know that in which direction it is going to move. It is something like this, that let's suppose it is one of the molecule, and I don't know that whether it will be moving in this direction, let's call this as a Vx, whether it would move in this direction Vy, or whether it could move in Vz direction. So we don't know. Exactly, we don't know the situation that where it will go. Either it could go Vx, or it could go Vy, or it could go in the Vz direction. But we don't have any idea. We don't have any idea there in which direction it is about to move. I hope this is clear. Is it clear? Yes. Next, the temperature of the gas. The temperature of the gas depends on the average kinetic energy in it. So it is only the kinetic energy depends on the temperature. Higher the temperature, higher the kinetic energy. It is something like that. And molecules obeys Newton's laws of motion. This all molecules are going to obey the Newton's laws of motion. I hope this all things are clear. Is it? Is it crystal clear? Are you sure? Are you sure? Great. Next. Next. The molecules move freely in a straight line, and when they are move freely in a straight line, this is the talk. This is what we are discussing before two successive collision. That means let's suppose one molecule is here, and next time it is going to collide with this, then within this two successive collision, it will always travel on a straight line. It is always traveling in a straight line. So this is traveling in a straight line, and they are going to follow the Newton's first law. This implies that the total momentum is conserved as usual, because when collision would be there, when collision would be there, total momentum is conserved. And as we have discussed, these collisions are considered to be an elastic. We can derive an expression for the pressure of a gas based on this assumption of the kinetic energy, as well as when this is elastic collision, that means this total kinetic energy is going to be conserved. I hope this is clear. Is it clear? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Great. Next, let's look at certain quick questions. Do it quickly. It says that which of the following is the assumption of kinetic theory of gases? First, gas consists of molecules. Yes. Collision among the particles are elastic. Yes. Pressure is constant in all direction. Yes. This all of this. Yes. This all are the correct. Next, the temperature. The temperature of the gas depends on which temperature of the gas depends. Does it depends on the average kinetic energy? I should say yes. Average potential energy, no, because they would be always in motion. If it is not belonging, or if it is not depending on the potential energy, so there is no case of dependency on the total energy. So average kinetic energy would be the correct answer. I hope this is clear. Is it clear? Is it clear? Now let's discuss the gas laws. That you might have discussed this in your chemistry classes too. Yes, we are going to discuss it one more time. Let's discuss it. Gas laws. So the behavior of a gas can be described in terms of the macroscopic variables like pressure or volume and temperature with the help of the gas laws. Which gas laws I'm going to discuss here? That this are the they are I'm going to discuss here the Boyle's law, Charles law, Gay-Lussac's law, and Dalton's law of partial pressure. So we are going to discuss this all laws. We are going to discuss all these laws one by one, and we get an idea that how a gas can behave when certain situations has been met. I hope this is clear. Is it clear? Is it clear? So let's begin with the Boyle's law. What does it says? It says that for a given mass of a gas at constant temperature, and the pressure of the gas varies inversely with the volume. So it says that if given mass, that means mass is constant, and temperature, a temperature is constant. Yes, these two are the constant. Look at this. Here the mass is not varying, even the temperature is not varying. Yes, and this represents the pressure, that as soon as you increase your volume, you can see this, as soon as you increase your volume, your pressure is decreasing. So it is the situation something like this. It is P versus V, as you can see from this as well. This is something like this. As volume is increasing, pressure is decreasing. It is something like that. I hope this is clear. Is it clear? Great. If I plot this with certain more details, because this is required. One more time. This is P, this is V. And if I plot this, then this are the curves something like this. Let's say this curves are called as the isothermal curves, and it represents the temperature. This is T1, this is T2, this is T3. When I say this is T1, this is T2, this is T3, this could be written as T1 is greater than T2, which is greater than T3. I hope this is clear. Is it clear? Is it clear? Please do remember this. Please do remember this. This is going to help us. This is going to help us in thermodynamics as well. So these are the isothermal curves, and this was the Boyle's law, that P is inversely proportional to the volume of the gas. Let's have a look to the next. It's a Charles law. In this situation, for a given mass of a gas, that means mass is constant, and at constant pressure, look at this pressure is not going to change. If the volume if the volume of the gas is directly proportional to its absolute temperature, so here in this case pressure is constant, mass is constant, and temperature is keep on changing. So if you are going to increase the temperature, look at this candle is started burning, and if candle is started burning, its volume is increasing. This is the situation. This is the V versus T graph. I hope this is clear. Is it clear? Is it clear? So let's plot this with some more detail in it. Then it could represent something like this, that this is volume axis, this is time axis, and this could be a certain lines that can pass through the origin, or I should make them pass through origin, because this has been represented as dotted lines. It is something like this. So these are the pressure lines, P1, P2, P3. Now I need to take a decision that which line would be higher, which pressure would be higher, which pressure would be lower. Yes, as you aware that PV is equals to nRT, this is the ideal gas relation, and this graph is of V by T, that means it is equals to nRP. So I understand that V by T, this is the slope of this graph, a graph of V versus T. This is slope of graph is inversely proportional to the pressure. So let's understood how to find out the slope of graph in this situation. I understand this is theta 1, this is theta 2, and this is theta 3. We always calculate the angle from the x-axis in the anti-clockwise direction. So I could feel that, even you could feel it, that P1 is greater than P2, which is equals to greater than P3. I hope this is clear. Please do remember this. Yes, I hope this is clear. Is it clear? Is it clear? Do you have any doubts in this? Is there anything? Is there anything? Now let's discuss the next law. It is the next law. It's about Gay-Lussac's law. So according to the Gay-Lussac's law, for for a given mass of a gas, at constant volume, and volume would be the constant, the pressure is directly proportional to the absolute temperature. So for a given mass of a gas at constant volume, the pressure is directly proportional to the absolute temperature. As you can see that This is P versus T graph. And when this is P versus T graph, as temperature increases, its pressure is going to increase as well. Is it clear? Is it clear? Are you sure? Do you have any doubts in this? Do you? Do you have any doubts? Is there anything? Is there anything? Are you sure? Are you sure? Do you have any doubts? No? Great. So now let's plot this graph with certain more information on the volume as well. That this is P versus T, and these are the curves having a constant volume. Yes, this is, let's say, V1, this is V2, and this is V3. So I want the detail. I want a detail about the volume 1, volume 2, and volume 3. How could I have it? How could I have it? And what it could be? What do you think? How can I do it? How could I do it? What do you think? So what I understood is that we have this relation. It's a PV is equals to nRT. And when I say it's a PV, when I say it's a PV is equals to nRT, what I'm supposed to do is it's a P by T that is equals to nR by V. And when I say it's a P by T is equals to nR by V, this is equals to, this P by T is the slope of this graph. It's the slope of this graph is inversely proportional to the 1 by V. To find out the slope of the graph, I need to make an angle theta 1. This is theta 2. This is theta 3. So it is the situation that V1 is greater than V2, which is greater than V3. So V1 is greater than V2, V2 is greater than V3. This is the situation. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any confusion up till now? Up till now, do you have any confusion? Are you sure? Are you? Do you understand this completely? Have you got this? Have you? Great. So now let's work for the Dalton's law. Dalton's law of partial pressure. It said that the total pressure exerted by a mixture of non-reacting gases, it's a non-reacting gases, they are not going to react within this two, occupying a vessel is equal to the sum of the individual pressure which each gas exert if it is alone occupies the same volume at a given temperature. So they said that, let's suppose we are having an n number of gases, then the pressure by an individual, let's suppose this is pressure by first gas, this is pressure by second gas, this is pressure by third gas, and so on, this is pressure by nth gas. The pressure given by all these gases is addition of the total pressure. It is for n number of gases. So where P is the pressure exerted by the mixture of the gases, P is the pressure exerted by the mixture of the gases, and this P1, P2, P3 and Pn, all these are the partial pressures of the component gases. I hope this is clear. Do you understand this completely? Do you understood this? Are you sure? Are you sure? Yes, no. Yes, great. So now ready for the questions? Do you? Do you ready for the questions? Let's have a look. Let's suppose if I have been asked that if pressure of a gas is increased 2 times, what should be the what should be the change in volume so that temperature and and number of moles remains constant. How will you do this? So what they are supposed to do, they have increased their pressure by twice. They have increased the pressure by twice, and they want that what should be the change in the volume, what should be the change in the volume, so that temperature remains the constant. So what I need to do is I need to do it's a P1 V1 is equals to P2 V2 according to the Boyle's law. And if I can do this according to the Boyle's law, P1 V1 is equals to P2 V2. I can have this relation, this is P1 into V, this P2 is equals to 2P into V2. So this is 2P1, sorry, this P1 has gone, and V2 is equals to V1 by 2. It is as simple as that. I hope this is clear. Is it clear? Is it clear? Are you sure? Can it be done by you guys? Can it be? Are you sure? Are you? Great. Let's work for the next question. Suppose the next question says that a is filled gas is filled in a container at 27 degrees Celsius. On increasing the temperature, on increasing the temperature to 127 degrees Celsius, 1 liter of the gas, 1 liter of the gas escape out of the container. Find out volume of the container. This is the requirement. How will you do this? What is to be done? So what is given is that it has been filled at 27 degrees Celsius. First task, that I need to convert this 27 to Kelvin, which is equals to 27 plus 273, which is equals to 300 Kelvin. uh, Now the next temperature, they said at 127 degrees Celsius. So again I need to convert this is 127 plus 273, which should be is equals to 400 Kelvin. And initially a gas was filled. Let's suppose initial volume is assumed to be V, and the final volume, what should be the final volume, that it said it's the 1 liter, and they said it's a 1 liter is approximately having 1/4 of mass. This has been given. So the final volume would be equals to initial volume plus 1 liter of gases. I hope this is clear. So according to the Charles law, I should proceed because I have been given V and T. So Charles law, it's a V directly proportional to the T, and when it is V directly proportional to the T, it's a V2. It's a V2 divided by V1 is equals to T2 divided by T1. So this V2, this is this V2, that would be equals to this is equals to V plus 1 divided by original volume V. This is equals to T2, this is 400 divided by 300, this has gone. So this is equals to 3V plus 1 is equals to 4V, and from this it's a 4V. This is equals to 4V minus 3V is equals to 1, and this is equals to V is equals to, this is equals to 3V plus 3. Sorry, I made a mistake over here. Yes, So this is 4V minus 3V is equals to 3, and this V is equals to 3 liters. This was the volume of the container. I hope this is clear. Is it clear? Is it? Are you sure? Any doubts up till now? No, because these are very easy question, but this kind of questions can be asked. Yes, this kind of questions can be asked. In the previous history, this has been asked. This has been asked. So please go through this once, and this will be yours. Next question says that the pressure of a gas filled in a closed container, filled in a closed container, increased by 1% when when temperature is increased by 1 degree Celsius. Find initial temperature of the gas. You need to find out the initial temperature of gas. How will you do this? So let's write what data has been given, and then we will see what could be done. So it says the pressure of a gas filled in a closed container increased by 1%. Okay, so let's understood that initially the pressure would be of P, and finally it would be a P plus, it would be an 1%. That means 1 by 100 of P. This is equals to 101 divided by 100 of P. Yes, this is P1 and this is P2. Now what else do you change? Its temperature has been changed by 1 degree Celsius, so it's a T1 is equals to T Kelvin initially, and this T2 is equals to T plus 1 Kelvin. Now look at this. It is the place where you can made a mistake, that it is increased by 1 degree Celsius. So basically this is a change in degree Celsius. And when degree Celsius has been changed, when degree Celsius has been changed by 1 degree Celsius, even it would be a change in 1 degree in the Kelvin. I hope this is clear. So change 1 degree change in Celsius is equals to 1 degree change in the Kelvin. I hope this is clear. So here you are not going to write it's a T plus 273. No, no, no. It is absolutely incorrect. But you are mentioning that it is has been changed. And when we say it has been changed, when I say it has been changed, it could be written something like this. I hope this is clear. Yes. So now we have a pressure, we have a temperature. So let's write it according to the Gay-Lussac. It is P, it is P directly proportional to the T. So I could write it, it's a P1 divided by P2 is equals to T1 divided by T2. And once I write this, it's a P divided by 101 by 100 of P, that is equals to T1. Initially it was at T, now it's at T plus 1. So this PP could gone, and this is 100 divided by 101. This is equals to T divided by T plus 1. So this could be, it's a 101T. This is equals to 100T plus 100, and this is 101 minus 100. This is T is equals to 100 degree Kelvin. I hope this is clear. Is it clear? Is it clear? So do you understand this completely? Do you have any problem with this? Do you have any problem with this? Do you? Are you sure? Are you sure? Are you sure? Great. So, can we move to the next quick questions? Can we? Let's have a look. It says that according to the Boyle's law, what we understood, we can understood that PV equals to constant. Yes. P is directly proportional to the 1 by V. Yes. P directly proportional to the V. No. So both A and B should be the correct answer. Next, necessary condition. Necessary condition for Boyle's law. For Boyle's law, it is P directly proportional to the 1 by V, where mass and temperature both would be the constant. So in my options, it is a constant temperature. So this should be the constant. Constant volume, no. Constant pressure. So this would be the answer. Next, V is directly proportional to the temperature. States which law? Yes, it's a Charles law. Boyle's law, what does it say? It's a P directly proportional to the 1 by V. Gay-Lussac, what does it say? It's a P directly proportional to the T. Dalton, it says P is equals to P1 plus P2 plus P3 up to Pn. I hope this is clear. Is it clear? Is it clear? Now let's look at this question. P by T is equals to constant gives the, yes, it's a Gay-Lussac. P by T is equals to constant, or I should say it's a P which is directly proportional to the temperature. Next, it's a total total pressure of a mixture of ideal gases is the sum of the partial pressures. This gives the Dalton's law of partial pressures, which is P is equals to P1 plus P2 plus P3 up to Pn. I hope this is clear. Is it clear? So do you have any doubts up till now? Do you? Do you have any doubts? Do you have anything? No? Any doubts? No? Great. So now let's move to the Avogadro's hypothesis. Yes, let's look. So what Avogadro said about is that equal volume of gases have equal number of molecules at the same temperature and pressure. This is what we call as the Avogadro's hypothesis. It says the equal volume of gases have equal number of molecules at the same temperature and pressure. So this helps us to understand the combination of different gases in a very simple way. This helps us to make a lot assumptions and lot calculation based on the Avogadro. So what is Avogadro number? What from this hypothesis he has given us one of the number, and what is it? It says that number of molecules present in 1 gram mole of a gas is defined as the Avogadro's number. And this Avogadro number, it is 6.02 into 10 to the power 23. It's a per gram per mole, or you can write it's a 6.023 into 10 to the power 26 per kg mole. It is just the variation of gram and mole. Now the question is, what is mole? Yes, because I am the physics faculty, how could I know what is mole? Then we have a definition of mole is that the mass of 22.4 liters of any gas, it's a mass of 22.4 liters of any gas, is equal to its molecular weight in grams at STP, that we call as a standard temperature and pressure. When I say standard temperature, it's a 273 K and pressure is 180. This amount of substance is what we call as a mole. So it is a mass of 22.4 liters of any gas, which equals to its molecular weight in gram. Its molecular weight in gram at STP. This is what we call as an Avogadro's number. I hope this is clear. Is it clear? Is it clear? Yes, so this is all about the Avogadro number. Now let's study one more scientist. He has given another things. I'm talking about the John Dalton. He was an English chemist, and when different types of atoms combine, they obey a very certain and simple law. This Dalton's atomic theory explains these laws in a simple way. So what it is, let's have a look. Kinetic theory of gases begins with certain postulates, and they describe the motion of that assumptions we have studied up till now. And when I studied the every law, I came to know that this is one law was P directly proportional to the 1 by V, and another was V directly proportional to the T. A same way another is the P directly proportional to the T. So if I merge this, I am having this relation. It's a P into V is equals to KT, where K is a constant. K is a constant for a given sample, but that can be varies with the volume of the gas. So when I say this, P is the pressure, V is the volume, and T is the temperature of the gases. I hope this is clear. So in the ideas of the atoms or molecules, K is proportional to the number of molecules. So we can write this K is equals to N into K, where K, a small k, is the same for all gases, and this is called as the Boltzmann constant. Generally it has been denoted by Kb. B is used as a subscript to represent its Boltzmann. So what I can write, it's a P1 V1 divided by N1 T1 is equals to P2 V2 divided by N2 T2 is equals to Kb. This is Boltzmann constant. So it means, if look at this carefully, this is something like this: PV by NT is equals to KB. If P, V and T are same, then N is also same for all the cases. This is Avogadro's hypothesis again, which states that the number of molecules per unit volume is same for all gases at fixed temperature and pressure. So if you fix pressure, if you fix temperature, and if you fix a volume, this N1 equals to N2. This is what Avogadro is calling about. Yes, that number of molecules per unit volume, number of molecules per unit volume is same for all gases, but for this, temperature should be fixed, pressure should be fixed, and volume of the container should be the fixed. I hope this is clear. Is it clear? Is it clear? Ready for some quick questions? Great, let's have a look. It says that equal volumes of gases have equal number of molecules at the same temperature and pressure. This statement is known as, yes, it's an Avogadro's hypothesis. Next, the value of Avogadro's number Na, that could be written as 6.02 into 10 to the power 23 per gram mole. This is the value of the Avogadro's number. Does it clear? Does it? Are you sure? Are you? Great. Now let's discuss about the ideal gas and real gas. What is this? So let's first begin with the ideal gas equation. It says that ideal gas equation that connects P, pressure P, volume V, and absolute temperature T, that could be represented as this PV is equals to mu into RT. This pressure into volume is equals to mu into RT, or even that could be written as it's a KB into N into T, where mu, what does it signifies? It signifies it is the ratio of m to the m naught. M is the where m is the mass of a gas containing n molecules, and m naught, it is the molar mass. So mu could be written as m by m naught, where m is the total mass or m naught is the molar mass that we call, or it could be represented as n by Na, where n, capital N, is the number of molecules, and Na, it's an Avogadro number. So ultimately this is the mole number, which could be represented by m by m naught, or n by Na. So if I replace this mu, and it's a PV equals to mu RT, where R are the universal constants. R is the universal gas constant, and Kb, it's a Boltzmann constant. Kb could be represented as R by Na, and the value of the Boltzmann constant, it is 1.38 into 10 to the power minus of 23, while the value of the R, it is 8.314 joule per mole per Kelvin. So this is ideal gas equation. This PV is equals to mu RT. Any doubts in this? Is there? No. Great. So real gases satisfy the ideal gas equations at low pressure and at high temperatures. Please do remember this. I am sure that you must know this, all this, because this has been studied in chemistry as well. But even though we are going to cover this, even though we are going to cover this, as no stone should be unturned. Let's understood that at low pressure and at high temperatures, all the real gases will behave as an ideal gases, and the perfect gas equation could be written as PV equals to mu RT. So we say that a gas that can satisfy PV equals to mu RT exactly at all pressure and temperature is defined as the ideal gas. And why this has been followed at low pressure and temperature? Let's have a look. At low pressure and high temperatures, the molecules are far apart and molecular interactions are negligible. And when molecules are not going to interact, they will behave as an ideal gas. So do you understand why we have chosen these conditions? Are you sure? Great. An imaginary gas, ideal gas, when we say an imaginary gas which possesses the following properties, that is called as the ideal gas. So how should it behave so that we can call it as an ideal gas? Let's look. It says that the molecule of an ideal gas are extremely small point masses among which no intermolecular forces should act. Next, it should obey the laws in all states of temperature and pressure. And one very good statement is no gas in the universe is an ideal gas. So ideal gas is just an hypothesis, or we should say it's an assumption, or let's suppose we can say that it is our standards that we have set, that if any gas is behaving as an ideal gas, then it should look like this, that we have set the standards, and we try that some gases try to achieve this as achieve this assumption, and that is what we call that. If they can achieve this, we will call them an ideal gas. I hope this is clear. Is it clear? Great. Now, what is real gas? A real gas are the one which does not obey the ideal gas equation. It's a PV equals to RT. But this gas do not obey the Boyle's law, which is PV equals to constant, and other gas laws also. This are not going to be obey 100%. 100% is what we call as the real gases which we deal with. I hope this is clear. Is it clear? So let's check difference between real gases and ideal gases. In real gases, though the intermolecular forces of attraction between molecules of a gas is very less, it is not going to be zero. Yes. So what happens in ideal gas? In ideal gas, the intermolecular forces of attraction between the molecule is zero. It is absolutely zero. But the problem is ideal gas does not exist while real gas exists. So our requirement would be our requirement will be always that my gas, that means my real gas, should try to achieve maximum possible what is said by the ideal gas. But no gas is perfectly ideal. That means no gas is going to perfectly suits the ideal gas. I hope this is clear. Now let's look at the certain equations of state for real gases, or we can say it's a van der Waals gas equations for 1 mole of gas. This, you must know this all rules. We are just pushing it to you so that it can be brushed up. So for 1 mole of gas, P plus A by V square into bracket V minus B, that should be is equals to RT. And if I replace this for the n moles of gas, this could be written as P plus A into n square divided by V square into bracket V minus NB. This is equals to n into RT. This equation is not at all universal, and real gases obey these equations at high pressure and low temperatures. And one more very effective, it's Boyle's temperature could be written as TB is equals to A by R into B. Have you got this? Do you understood this? Any doubts, any confusion up till now? Is there anything? Do you have any doubts up till now? Is there? No? Great. Now let's look at this. Ideal gas satisfies the equation which is equals to PV equals to mu RT at all pressure and all temperatures. Yes, these are the ideal gas. They are going to follow each thing, everything. Next, real gases blank the ideal gas equations. They are not going to obey the ideal gas equations anyhow. Next, when when does real gas behaves like an ideal gas? At high pressure, no. At low temperature, no. At low pressure and high temperature. Why? Because at low pressure, because at low pressure and high temperature, their force of interactions is very less. So as their force of interaction is very less, they can behave as an ideal gas. I hope this is clear. Is it clear? Is it clear? Are you sure? Now any do you have any confusion up till now? Is there anything? Is there any confusion? Are you sure? Are you sure? So ready for certain quick questions? Are you sure? Let's have a look. Suppose the question said that suppose 1 mole 1 mole of each of hydrogen, oxygen and nitrogen are mixed in a closed container of volume 10 liters and temperature 27 degrees Celsius. Find pressure exerted by the mixture. How will you do this? So basically we have a mixture of three gases. We have the hydrogen, we have the oxygen, we have the nitrogen. And what I need to do, I need to find out the pressure. So basically according to the Dalton's partial pressure, it is P is equals to P1 plus P2 plus P3, and this P could be given as a mu1 into RT divided by V plus mu2 into RT divided by V plus mu3 into RT divided by V. As I understand this, they have given 1 mole of an each of gas, that means mu1 equals to mu2 equals to mu3 is equals to 1. The temperature is same, the volume is same. So what I need to do is this is equals to P is equals to 3 into R into T, total number of moles are 3, divided by V. When it is something like this is 3R, it's an 8.314 multiplied by temperature, it was 27 degrees Celsius, so it is 300 Kelvin. Now you understand. And volume, the volume of the container, they said it's a 10 liter, so this will be a 10 into 10 to the power minus of 3. If I solve this is 3 into 3, it's a 9 into 10 square multiplied by 8.314 divided by, this is 10 into 10 to the power minus 3, this is 10 to the power minus 2. So if I solve this, it is 7.48 into 10 to the power 5. As they have asked about the pressure, it's a Newton per meter square. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you understand this very clearly? Are you sure? Are you? So ready for the next question? Are you ready? Let's look at this. Now what they have done is they have two identical containers, something like this. And in this container, let's call this container A, this container B. This is pressure P1, this is temperature T1, this is pressure P2, this is temperature T2. These two containers are connected like this, and initially this valve is closed. It is something like this. So it said that it said that these are the identical containers that I initially said. It's an identical container. So they said if this valve is open and and if this valve is open and the temperature of this containers are maintained and not allowed to change, not allowed to change, find out find out pressure of the mixture of gas. So how will you do this? They want pressure of the mixture of the gas. They said that two containers are there, and they in this situation initially this valve is closed, so there is no exchange of the gases could be possible. Now what they want that now if I'm going to open this valve, then the situation would be there could be a possible interactions between two gases is possible. And if this interaction is possible, the gas from one section to other section would be allowed to go. And if this is allowed to go, what should be the next temperature, what should be the next pressure of the gas? So what I understood is that let's suppose you can use conservation, or I should not say conservation because this was not the law, but what I understand is N1 plus N2. This was the situation, number of moles of first container plus number of moles of second container when valve is closed. That should be is equals to N1 dash plus N2 dash. This is the situation when valve is open. I hope you understand this. So N1 plus N2 could be written as N1 plus N2 could be written as N1 dash plus N2 dash. So when I write it's an N1 plus N2, this is equals to N1 dash plus N2 dash. We always know it's a PV equals to nRT. So from this N equals to PV by RT. So what I need to do is it's a P1 V divided by RT1 plus P2 V divided by RT2. No need to write V1 V2 because they are the identical containers. This is equals to P dash into V divided by R into T1. Now here they have said that the temperature of this containers are maintained and they are not allowed to change. So I cannot write here it's a Tx, it would be a T1 because temperature would be maintained, plus P dash V divided by R into T2. If I'm allowed to do this R has gone, this V, this has gone. So this is equals to P1 by T1 plus P2 by T2, and that should be is equals to P dash into bracket 1 by T1 plus 1 by T2. It is something like this. If I try to solve this, it's a P1 T2 plus P2 T1 divide by T1 into T2. This is equals to P dash into bracket T2 plus T1 divide by T1 T2, and this has gone. So from this situation it is P dash that should be is equals to P1 T2 plus P2 T1 divide by T1 plus T2. I hope this is clear. Is it clear? Is it clear? Do you understand this? Have you got this? Are you sure? Are you sure? Can you handle this kind of question? Will you be? Will you be? Great. This is one of the pattern of the questions, that when mixtures would be there, this is the best suitable approach, because if container is closed enough, and then the total number of moles will be always same. Ready for the next question? Are you? Can you do this? Great. Let's have a look. It will say that an ideal gas is obeying the equation, that is T multiplied by root of P is equals to constant at STP. It's a standard temperature and pressure. Now they said if volume of gas changes from V to 8V, find final temperature of the gas. So how will you do this? Look at this, what they said. They said that ideal gas is there, and that ideal gas is going to obey the equation, which is T under root of P would be equals to constant. And when I say it's a T root of P is equals to constant at STP, and they said a volume of the gas is changing from V to 8V, and I need to find out the final temperature of the gas. So first observe this situation very carefully. What they said is that their initial volume was V, their final volume was 8V, their initial temperature, it's they said it's a STP, standard temperature and pressure. Initial temperature it's a 273 Kelvin, and the final temperature I'm looking for. But the relation is, it's a temperature multiplied by root of pressure is equals to, let's say, K. It's a constant. So what I want, I need a relation between V and T, but I have been provided the relation of T and P. It's a temperature and pressure. So what I understood is that that's why they write an ideal gas. Yes, this is the word where freedom has been hidden. An ideal gas, when they said it's an ideal gas, I am allowed to write it's a PV equals to nRT. I hope you understood this. Now what I want temperature and volume. That means what I don't want, it's a pressure, so I need to replace that pressure. That's it. So pressure could be replaced, it's an nRT by V. You understand, N and R is constant, so only need to write T and V. So this is T multiplied by root of T into V is equals to constant. This could be written as, how could I write this? This could be written as, this is equals to T to the power 1, this is T to the power half, this is V to the power half is equals to constant. Yes, so this is T to the power 3 by 2 divided by V to the power half is equals to constant. Yes, this is good enough. I hope this is clear. Is it clear? Is it clear? If you want, you need to square this. That's why this will look pretty good. If I square this, it's a T cube directly proportional to the V. Yes. So now this is my new relation. And now I am having a data, I will easily do it. Let's do it then. It's a T2 cube divided by T1 cube is equals to V2 divided by V1. So this is T2 cube divided by T1 cube. It's a 273 cube. This is equals to V2. It's an 8V. This is V. So if this is the situation, this has gone, and this T2 cube that should be is equals to 8, which is 2 cube multiplied by 273 cube. So this T2 could be written as 2 multiplied by 273, which should be 546 Kelvin if options have been given in Kelvin. If not, then 273 degrees Celsius if options have been given in Celsius. I hope this is clear. Is it clear? Is it clear? Are you sure? So this kind of questions can be asked where the keyword would be the ideal gas. If they have written this, you are allowed to do this. And if you are allowed to do this, no task is difficult. Have you got this? Have you got this? Are you sure? Are you sure? Now ready for a very good question. Are you? Are you ready for a very good question? Are you sure? Great. Let's have a look. The question said that let's suppose this is one of the container, and in this container we have at one of the end a certain piston kind of thing has been arranged. So the question says that a gas is enclosed in a vessel having in a vessel of volume V and and pressure P. Now it says it is being pumped out. It is being pumped out of the vessel by means of a piston pump. By means of a piston pump with stroke volume with stroke volume of V by 10. They will ask what would be the pressure, what would be the pressure in the vessel after after n strokes of the pump. This is the question, that this was the container and this is having filled up with the gas, and this volume is V, and let's suppose this is a small v, or I should say V dash. So every time it is there, and it is going to remove the V by 10 amount of gas after one stroke, and you need to find out the pressure in the vessel after n strokes of the pump. So what I understand is that during the first stroke, during the first stroke, initial volume it's a V. The final volume that should be is equals to V plus V dash. When we consider the volume, it is not the volume of the gas, it is the volume of the container in which it has been filled. I hope you understand this. Have you? Have you understand this? When I write that volume is there, its initial volume would be V, final volume will be equals to V plus V dash. So if I write according to the Boyle's law, if I write according to the Boyle's law, here one more thing can be written, that temperature remains constant. In this situation, temperature remains constant. So what I can write, it's an P into V, which was initial situation, that would be equals to pressure after first stroke, sorry, multiplied by V plus V dash. So this P1 that could be written as P multiplied by V upon V plus V dash. This V dash is equals to V by 10. I hope this is the situation and this is clear. Are you, have you got this? Now, now the critical part has arrived when you are about to stroke it one more time. But before you stroke it, that stroke, after the first stroke, gas that has been remain in the container will occupy complete space of container. Do you understand what I mean? That when and when this situation happens and you have first stroke applied, and when you have first stroke applied, that means you have removed 1/10 of the original volume of the gases. So it is not like that, na, that the remaining gases will not occupy that space. Again, now our gases will occupy the complete space of the container. And when you are going to use the complete space of the container, a situation would be that now, even now situation would be that it's a P1 into V, because pressure is P1, that should be is equals to P2 into bracket V plus V dash. This is the situation after second stroke. This is the situation before second stroke. So this could be written as P2 is equals to P1 into bracket V upon V plus V dash. Now this will continue. I hope you understand this. That again I apply a third stroke. Before the third stroke, the remaining volume of the remaining molecules of the gas will contain the total space of that gas, and when they will contain the total space of that gas, the new volume will be the V that I have written over here. So if this will continue, this is, let me replace the value of P1. The value of P1 was, it is something like this, value of P1 was equals to, this is equals to P into bracket V upon V plus V dash. So if I replace this, this could be written as original pressure P, initial pressure, what I can say, it's a V by V plus V dash multiplied by V plus V dash. So this could be written as P into bracket V by V plus V dash whole square. This is just this situation after I have been pumped out second times. So if it has been n times, this is equals to P into bracket V by V plus V dash to the power n. This is the pressure at nth times. I hope this is clear. This is very good example. Please have a focus on this and work on this. I hope you understand this. Do you understand this? Have you, do you have any doubts, any difficulties up till now? Do you have it? Do you? No? Great. So let's wind it up the session over here. This was the assumptions before we study the KTG. It's a kinetic theory of gases, and we have also covered the laws of the KTG: Boyle's law, Charles law, Gay-Lussac law, and mainly Avogadro hypothesis. But as well as we have also discussed about the real gases and the ideal gases. So please revise this. Please go through even the theoretical aspects of this, that when any real gas can behave as an ideal gas, or when any real gas can behave according to the different laws, when it can behave, when it cannot behave. If real gas behaves as an ideal gas, why it is behaving like this, why at high temperature and low pressure and everything. Please go through this. This is requirement of the competitive examination. That's why only I have covered it. Please understand this. Please go through it. Make a question based on this. This will help us. Thank you. Have a good day. Take care.